All right, so for the homework assignment, we were to go in and right now we're assuming our rebalance is left-left. Well, we probably need to find out what our rebalance is, right? Whether it's left-left or right-right. Those are the only two we currently support. So what we can do is when we rebalance our list, or rebalance our tree rather, each time we add something to the tree, we can go ahead and call rebalance, and rebalance could choose to rebalance if it was out of balance. Make sense? So we can kind of consolidate everything into this one function. So the first thing we'll do is we'll ask if it's out of balance. So I'm going to go ahead and make this guy private now, so we can't access it externally. So when we call rebalance, we'll ask the question, if this dot is out of balance, then we need to do some rebalancing. Okay? So we'll go ahead and just for the sake of argument, we'll do a println out of balance, like that. Then we need to determine how we are out of balance. All right, so with that, we passed in a char for the dude that was out of balance. What we can do for right now, just to keep this equivalent, we'll say char C gets passed in there. Because later on, we're going to have to probably keep track of the guy we're adding. All right. In fact, actually, why don't we just do that now? That'll be, since we're already using our singleton. So when we add something to our binary search tree, we're adding this. We're going to go ahead and in our singleton, let's create static char last entry. All right, and this guy will start off as the question mark, let's say. And when we add something in BST, we'll go ahead and say BST core dot last entry is equal to payload. That's the dude we were last adding. Okay? At least in our current world. All right, so now we're remembering the last guy that was entered. We don't need to rehash that. So back to our rebalance. So if we're out of balance, something went wrong. Now we want to know how we are out of balance. So here's our function for how we are out of balance. And right now it takes a char as a parameter. Well, let's go ahead and make this guy private. He no longer needs to take in a parameter because that parameter is stored globally for the last guy that was added. All right, so what we can do is we can say char val is equal to BST core dot last entry. All right, so we'll just go ahead and grab it from our singleton so we have it local. I threw it in a variable here, that way we didn't have to rewrite the rest of the stuff. We still have a variable named val. All right, so we want to know how we're out of balance. Now, right now we're printing out how we're out of balance. We just separated the guy with a dash there. So what I'm going to do is we're going to make a guess that we're out of balance to the right, switching it to the left if we are. We're going to change this guy to return a string. All right. So we're going to switch this guy to return a string rather than printing stuff out because our rebalance function needs to know how we were out of balance. All right. Right now we're spitting out to the screen how we're out of balance. We need that other guy to know how we're out of balance. So we're building this out of balance initial, then we're adding something to it for out of balance secondarily. Ultimately, we are printing out this guy. So what we're going to go ahead and do is we're just going to return that guy. All right, and we'll take the little spaces out for no good reason. All right, so we'll build how we're out of balance, and we're going to put it in a string initial dash secondary. So we know it'll be all lowercase, so it'll either be left, left, right, right, left, right, or right, left. Those are our 4 different options. Right now our rebalance only works for 2 of them. So we're going to say if, well, let's go ahead and say string how is equal to this dot how are we out of balance if how dot equals left dash left. We're going to do the stuff we did before. Else if how dot equals right dash right, we'll do the right right adjustment. So this is essentially where the logic for our homework should have gone. Now you didn't have to consolidate everything in like we did. This just kind of makes some sense for us at this point, seeing that we've written these other things. So we've made it is out of balance and how are we out of balance private. For one thing, a binary search tree only needs to, he's the only one who needs to know about those guys. That's one advantage of doing that. The other advantage is it'll expose our errors in the other place so we know where we need to fix stuff. Because we were previously calling these 2 methods someplace else. So we were actually doing that inside of main activity. So it's no longer happy about this stuff. So here's our tree add stuff. After each add, we're going to go ahead and say tree dot rebalance. All right, we'll try to rebalance our tree. So we're going to go ahead and take all this stuff out. All right, and we want to produce a right out of balance for our example here. So G will go first. F goes to the right of that. F will go to the right of that, right? So that'll be G, F. No, it's the other way around. It's the alphabet. It's kind of an important thing. So A, B, B. That'll be out of balance to the right, correct? That's right, right? All right, so I'll start early in the alphabet. It's easier. No, that will be. A, if A is the root. Oh, this would be right, left. Yeah. I gotcha. Yeah, we don't support that yet. I get it. All right. So this will be right, because C is greater than B, B is greater than A, so it goes right. All right, makes sense. I was testing you. All right, so this should be out of balance, right. Let's go ahead and have our binary search tree print some stuff out here for us. So if we're out of balance, we're going to do some stuff. So we're going to go ahead and say system.out.println rebalancing left for that one. And we'll do rebalancing right for this one. All right, so we'll know how we're rebalancing stuff. Okay. So each time we add something, we'll call out of balance. This is only if we're out of balance. If we're not out of balance, we'll throw an else in here. System.out.println tree is not out of balance. Okay. So the first 2 times through, we should see tree is not out of balance, and then we should just see rebalancing right. That'll be our proof that our new consolidation is doing what it's supposed to do. Okay, so main activity is going to add A, then add B, then add C. So A and B, we're still in balance. C is going to say, okay, things have gone south. We need to fix it. So we'll go ahead and run this. Okay. All right, tree is not out of balance, then right. Okay, so we know we're in the correct place now. All right, and just to further test this, after we've done whatever rebalancing we're going to do, let's go ahead and call this dot rebalance again, and hopefully it shows us that everything is legit. So that'll give us the additional feedback that it's no longer out of balance. So actually, rather than do that, let's just do a test to make sure the tree is fixed. System.out.println. After rebalance, this dot is out of balance. So we should always get a false after each rebalance. So let's go ahead and just quickly test this on left to make sure this is all working. So main activity, so we need to do CBA. That should be left. Okay, so we'll make sure that we've consolidated our left rebalance correctly. So we should get tree is not, then it'll say out of balance, rebalancing left, and then after rebalance, false. All right, seems to be doing its thing. Okay, so now we'll go back to our ABC, run this again, but we should see after rebalance it's still true because we didn't actually do any rebalancing, we just talked about it. All right, after rebalance, true. Okay, so now let's go and actually write our rebalance for right. All right, when we looked at our rebalance for left, what did we do? We're already keeping track of parent and grandparent and pivot and all of those guys. So these were the differences that we did. So let's go and draw our picture. All right, so now we have with ABC. All right, so our pivot will be B. Our parent will be A, which is also our root. Our grandparent will be null. And here's our culprit, the guy that actually threw it out of balance. All right, so when we did this for left, we asked if our grandparents was not null. We need to do something, but right now our grandparent is null. So we'll go into the else. So what are we going to do? We're going to set the root equal to our pivot. So that's that. Okay, so far so good. Then, what did we say to do? We're going to set our parent's left tree to null. Okay, in this particular case, we're actually setting our parent's right tree to null. Okay. So actually, let's just copy this stuff so we make our modifications. So set right tree to null. Okay, and then we added our parent to our pivot. All right, so here's our parent. We'll drop it onto our pivot. It should fall to the left naturally, right? And then our tree should be rebalanced. All right, so set right tree, add. So the algorithm difference between left left and left right was just one piece right here. Okay.
Under the if statement, the set left tree is not supposed to be set right tree.
Oh, this should be set right tree. Yep. We were still in the else, but you're right. This is if our grandparent is not equal to null, and we'll look at that example here in a second. All right, so in our current example, our grandparent would be equal to null. So we'll go ahead and run this. So after our rebalance, we should be set to false after rebalancing right, right. All right, so seem to fix that guy. Now we need to create a situation where we do have a grandparent. So go back here. So before we add the C, let's add an A and then a C, D. That's right. So that'll be out of balance, but we do have a grandparent now, right? So A is to the left, then we have a C and a D. So let's go back here. So we have another one of those. That guy's out here. And then we have a D down here. So now this is the culprit. This is the pivot. This is the parent. This is the grandparent. All right, so in that event, what do we do? Well, now our grandparent is not equal to null, so we're going to set our grandparent's right tree to the pivot. So our grandparent currently points to our parent, but we're going to move basically this stuff up here for the new right tree, I guess. Well, let's get this guy out of the way. That guy sort of in limbo. So there's our right tree. Technically, this parent still points to this guy, but we're about to fix that. Go back into our code here. Then what do? We set the parent's right tree to null, so that's now disconnected, so it actually looks like the way it should look here. And then we go ahead and drop the parent onto our pivot, which should have it drop right here. So now that tree is rebalanced. Okay, so there is rebalancing right, right. Seems to work for whether or not we have a grandparent or not. All right, questions about that? All right, so now let's look at the difficult ones. So right, right, left, left are the easier of the solutions. So now let's get ourselves a situation where we are left, left. Here, I want to, just to get this organized a little cleaner, I'm going to move parent and grandparent all off to the side. We'll just draw the arrows in when we need to. Keep track of the root of the tree. There's our pivot. There's our culprit. We'll just throw a root over there so we can always make it point. All right, so let's go ahead and let's create a scenario where we are out of balance right, left. Okay. So that would be A, B, C, C. This is to the right-hand side, but the last move was to the left. All right, so draw our guys in here. There's our culprit. There's our pivot. There's our parent. There's our grandparent. And we'll see if these guys currently hold up. All right, so when we have a left-right out of balance, the very first thing we need to do is create a right. I'm sorry, we have a right-left out of balance. I don't remember if I said that or not, but let's whatever. When we have a right-left out of balance, the very first thing we need to do is convert that into a right-right out of balance. And then we already have the solution to fix it, right? All right, so we need to turn it into an out of balance that we already know how to fix. So let's go back to the pictures here. Let's call this ABL tree. All right, so here is our right-left case. So the very first thing we did is we pivoted around the 5, around the parent. So we dropped that down, making, so as it currently stands, this is pivot, this is culprit, this is parent, and then grandparent is somewhere else. Doesn't really play into this situation. So what we need to do is we need to make pivot the culprit's right child and make parent's right child point to culprit. Now, if we do that, does everything else fall into place? Keep in mind we might have more tree down here depending on what this guy looks like over here. But at the end of the day, 5 drops down. 5 becomes, so this is pivot. Pivot becomes culprit's right child. Keep in mind that parent still points to this guy. So I'm actually, for the moment, I'm going to draw in the pointer arrows. Just so we can keep track of who still points to who. Okay, so this guy looks like that. So we need to make culprit, well, if we go back to this. This is culprit. We need to make pivot become culprit's right child. All right, so how do we actually accomplish that is the question. If we take our culprit, we know this was the last guy that was added if we're out of balance, right? We can physically set pivot as our culprit's right child. So let's look at that. So we're going to take this guy and we're going to set him as the right child of our pivot. Is that an accurate tree? Having the right child of C, B, C? Does this need to be, does this need to be an accurate, does this need to be an accurate tree? Is I guess the bigger question here. In this case here, when we move the 5 to the right of 4, that's legal because it's greater than. But what about moving a 4 to the right of 4? That breaks our tree rules, doesn't it? right? So let's go down this rabbit hole. So we're going to add this guy as the right child. Now, by forcing him to be the right child, as opposed to saying, well, we're going to take pivot and we're going to add him to culprit, he'll drop down to the left. And now we're right back to where we were before. All right, so we really can't add him. We need to force him into this position. All right, so we're going to take our, so this is if we are dealing with a right-left scenario. So let's follow the rabbit hole here in our code. Else if it is right, left, rebalancing right, left. Okay. First thing we'll do is we're going to take culprit and set his right child to pivot. Sorry, what we call it, BST core dot culprit dot set right tree to BST core dot pivot. Okay. Now this guy is still pointing down here. So what we need to do, and this guy technically is still pointing up here. All right, so we kind of have a day one Apple Maps type scenario. Ever see those pictures? Yeah, when Apple Maps first came out, there was some like really, like I don't know, look like a apocalyptic type nightmare type things where like it made roads. Here, let's see this road. It's worth looking at. Funny Apple Maps glitches. That would be a fun road. So, the way it was rendering different things, and there was some worse ones than this. But, you know, I mean, so that got all stretched out. Here's a road laying in a river. I don't think that's how that road works in real life. But, yeah, there was all sorts of stuff like that. They had roads going through buildings and that kind of stuff. So, yeah. Day one of Apple Maps kind of set it up to not be a great competitor with Google Maps. But all right, so we're going to need to patch this up a little bit. We really need to have our parents' left tree now point to our parents' right tree point to culprit. So BST core dot parent dot set right tree to BST core dot culprit. Okay, then we need to say BST core parent needs to get set to null. BST core dot parent dot set left tree to null. So that was the original left tree, which pointed back to this guy. This was the left tree of our parent. All right. I need one of these arrows here in a second. All right. No, we don't have that yet, I don't believe. So finally, we need to have culprit point to parent as the right tree. Did we already do that? Culprit, right tree. Okay, we already did that. I'll point to pivot, rather. All right, and pivot's still pointing down here. Let's recap that real quick because I think I was confusing parent and pivot while we were writing this. So we set culprit's right tree to pivot. we set our parent's right tree to culprit. That's correct. That's the guy that was above parent. We set pivots left tree equal to null, not parent. This guy down here was pivot. Okay? So now we have this guy set up, even though it looks a little wonky. This is a right-right type setup with one major problem. What's our major problem? Okay, so pivot points to the wrong place and culprit points to the wrong place. So those guys need to be flip-flopped. Right? If we try to rebalance this right now, it's going to screw up our tree because our global pointers are no longer pointing to the right place. Okay, these guys are both binary trees, so we're going to need a temp to do that. So we're going to go ahead and say swap pivot and culprit in preparation for right rebalance. So we're going to say binary tree temp is equal to bst core dot culprit. bst core dot culprit is equal to bst core dot pivot. And then bst core dot pivot is equal to temp. So that should swap those two dudes. So now pivot will point here, culprit will point here, and are we now in a position to do a right rebalance? All right, so what is a right rebalance going to end up doing? It's going to pivot around the C, correct? And this guy is going to do what? So if we have our list look like that, we need to make sure that what we have in the end is a legal binary tree. Okay? All right, so once we are back to our right case, what ends up happening? In this particular case, the 4 is going to bounce up to be the new root. So when we're pivoting, it's like turning that knob. We want to make sure this guy ends up as a legitimate tree. So looking at this picture here, actually we're only one level down. So looking at this picture here, if this is our pivot, B is going to drop down to the left of C, correct? So the way this will ultimately look is with the C hanging off the A. Is this what our final tree would look like in that particular case, our rebalance tree? Is that going to be a problem? It's not a legal tree, is it? Not by our definition. All right, so, well, we could say, well, maybe we say that everything to the right of our root node is greater than or equal to, and everything to the left is less than. Well, does that fix the problem? Well, let's see. So we'll pause that. That could be a potential fix. But now let's go and look at what a left-right problem would look like. Okay? So I'm actually going to copy this slide. And let me get rid of those things for a moment. We need to have it as the 2 C's to show my point right now. Yeah, the ABCD fixes the problem. There isn't a problem if we have ABCD.
Right. Because when there's 2 letters that are the same, but I'm getting mixed up with which C was added last.
this was the original added last C. This was the C that was before that. But that's kind of unimportant right now. What's important right now is that if we do our normal right fix, we'll be left with a tree that's not a legal tree by our current definition. Because our current, and we can't show that with a D. If we have a D here, it'll be a legal tree again, won't it? You know, so if we make this guy a D, let's see, actually it wouldn't have been out of balance then, would it? Well, it would have been, but it would have been out of balance differently. No, the C would have been to the left. So if this guy was a D and we fixed it, it's going to bounce back up where we have C, B, D. And that's a perfectly legal tree. Because that is greater than C. This is where it's no longer a legal tree. All right, so we need the CC example right now. If it was a D, we're good to go. Okay, but we need that CC example in order to show that our shifting to make this guy prepared for a right reversal breaks the rules of a binary tree over here. So then what we're presenting here is one possible fix. Is change the rules of our tree to allow, well, to be everything to the right of root is greater than or equal to root. Everything to the left of root is less than root. Right, so basically just switch where the equal sign is. That fixes it on the right-hand side for us, because if that's the case, then all of a sudden, this guy's a legal tree. Like, oh, C is greater than or equal to C, we're fine. This is all cool. But what's going to happen when we look at a left-right scenario and we rebalance? Are we going to be back into the exact same boat? So let's go down here. Let's unhook these guys, and we'll go ahead and write the algorithm for left-right while we're at it. That way when we fix it for one, we'll fix it for both. All right, so we have A, B. Actually, we're probably going to need let's do C. And again, we're still less than or equal to the left. So then we'll say this is B. And we'll say this is A. B is less than C. A is okay. Oh, wait a minute, but we need this to be Did I create the scenario correctly?
Do like C, B, B, C.
C, B, B. C. Wait, hold on. Oh, it'll be.
The B would be to the left.
Then the C is to the left of the B. The B. Yeah.
Or you could throw another C on top of that.
See here?
No, if you did like C, B, B, C, C.
And then we just need to throw crap on the other side. C, B, What's the next one?
B, and then CC.
That'd be greater than.
What would, what? I'm just making this worse.
Yeah, this would be less than.
Well, the first C would fall to the right of the first B. No, it's in the main. I don't know what I'm talking about.
Yeah, we're stuck in a loop. All right, so, well, but actually this could be good. So let's mess with this for another minute. But we're finding it difficult to create a left-right scenario. We can make a left-right scenario. So we can have a C, B, actually it would be C, A, B would go here, right? So that's a left-right out of balance. Okay, so if we just play that game for a second, to bring this guy back into balance, we need to make this a left-left. So that, so let's write the algorithm for that real quick. So this is grandparent points nowhere, parent points here, pivot points here, culprit points here. All right, so we need to turn this guy into left from its current left-right. So how does that compare to what we did over here in, so this is right, left. This is left, right. Okay, so in a left-right scenario, we need to put this into a left-left scenario. So we know that we're rotating about B. So what do we need to do? We need to set parent's left node to culprit. Actually, we did the culprit one first, so let's go ahead and do that first. So culprit's left node is going to become pivot. Okay, so we'll go ahead and drop this guy down here. And here's pivot. This guy still points here, though. Okay, so culprit's left tree becomes pivot, and then parent's left tree becomes culprit. So we'll just shift it up a little bit for a second. So that's essentially that. So now we look like left-left. We just need to finish disconnecting some stuff. Then pivot set right tree equal to null. And then we need to swap pivot and culprit. So we'll do our same swap. All right, so that puts us into position to do the correct rebalance. Okay, so now it looks like this, and we can do our normal left-left rebalance, and it would be a legal tree, correct? Okay, so that looks fine, as it would have looked on the right-left scenario had we given it a legitimate tree. So now if we back up for a second now, we'll spend another minute on this. Can we create a left-right scenario where we have something that's going to produce a tree that's not a legal tree when we rotate it. The only way to do that is to create a scenario where this is the same as this, right? Okay, and under our current rules, that's not possible, is it? Everything to the right of a node must be greater than that node by our current rules. So we could not have an A here. It's an impossibility to have an A there. Well, it's the wrong tree. Our tree would be broken if we allowed to have an A there right now. Right? We were able to do that on the right-left scenario because of how we had our rule set up. All right, well, so let's pause there for a second. Let's assume we switched our rules. And our rule said that our tree is going to have everything to the right of the root node is greater than or equal to it, and everything to the left is less than. Just switching where the equal sign is. Okay, no big deal. Can we create a right-left scenario following those rules? So let's disconnect stuff here. Okay, so C is greater than B. Well, it's greater than or equal to B because we're under the new rules. Actually, what we can do is we can say D, then C. We're okay there. Can we create a scenario here on the left where we get any legal tree? We couldn't on the other side. Back over here, if we change the rules and I want to have, because now we can have an A is allowed here, right? Let's go back to that. So if we say that everything to the right is greater than or equal to everything to the left is less than, this is now a legal tree. All right? So we can create the left-right imbalance using that, which then allows us to attempt to do our algorithm where we drop this down to this. Temporarily, this looks like an illegal tree. And that's okay, as long as it's just, we're just passing by. We're allowed to have partial illegal trees as long as it's just in transition to ultimately a legal tree. And then, ultimately, this guy would drop down to that, leaving us with still an illegal tree. All right, so flipping the rules doesn't fix the problem. All right, so we're back to our same problem. We can create left-right and right-left scenarios that leave us with illegal trees. How do we fix this? Would you agree that an illegal tree is a bad idea? If we're rebalancing our tree, we certainly don't want to break our tree, because the whole purpose of a binary search tree is for the tree to be organized, trustworthy, right? We can't all of a sudden have things to the left that really should be for the right just because that's how our rotation worked. A rotation can't leave our tree in an illegal state. So, go back and look at this picture. Notice the examples they've given us are benign examples. Our algorithm works just fine as long as you've given it a tree that doesn't have things that are equal on the wrong side. Our current algorithm works. So do we have to have a special case? Let's think about what that special case might look like. First, let's just confirm that this works in all cases where we don't have those matching guys. All right, that way we can ask the question, is pivot and culprit, are their payloads the same? If they are, special case time. Okay? So let's just make sure that if we have, so now we're back to our original model since we decided that the greater than or equal to thing didn't really make anything any better. So our original decision on where to put the equal stuff seemed to have no impact on the big scheme of things. So it's not like we made a mistake. All right, so we'll go back to our original model. So this guy would be a B then in this example. Okay, so this is a normal left, right out of balance. We did our drop down thing here, our move here. Then we did our rotate here. Is that a legal tree? Yep, we're cool with that guy. So, we can assume that this works for, let's just say, everything. Let's make sure it'll also work for our, in a situation where we have a grandparent. So let's see, this will be, let me bounce back a couple of levels. There we go. So there's our CD. So that'll be left. I want to get it where we have a grandparent that's not equal to, that's equal to something. I want grandparent to be the root node. All right, so this is, we want to have a left, right, so we need to go down twice. So that'll be another B. Do it. C is less than or equal to, A is less than or equal to, B is greater than. Yeah, so that's a left, right out of balance. That's legal. All right. It's not funny that the hardest part is coming up with examples that are that legitimately are broken trees. All right, so that will be grandparent. That'll be parent. This will be pivot, and this will be culprit. Okay. So now we want to make sure our previous example still works. So grandparent doesn't even come into play. We need to make this guy a left. So we drop pivot down. We move this guy up. We do the little swappy thing. Parent's left child gets set to culprit, so on and so forth. So our tree is left like that. Okay, is this a legal tree? C is less than C. B is, well, less than or equal to C. B is less than or equal to C. A is less than or equal to B. We're legit. All right, and trust me, it would mirror on the right-left side as well. So our algorithm is legit as long as we don't have our special cases. Okay, so it's what we need to focus in now is in our special cases. So let's go ahead and write the if statement for that special case. So we've determined that our special case, well, before we write the if statement, let's produce our special case. So we'll do it on the, where am I? I'm on the left side, right? Or the left right side right now. So let's go back here. Actually, we couldn't produce it on that side. We'll have to do it here on this side. Okay, so that's right, left, like that. So that's right, left out of balance. C is greater than B. C is less than or equal to C. All right. So this guy, when we try to put him into a right scenario, we drop this guy here. So these guys are still pointing. We move this guy up here. This guy's still pointing. Then we reconnect these guys up. So this guy now points down to there, and this guy points to null. We do our swappy dealy. So we still have, even though we've swapped them, pivot and culprit still are pointing to things that whose payloads are the same. So this is our bad case. This is an illegal tree. So we could ask the question if after we do our initial fix, if they're the same, we need to do special case stuff. So the question is what is that special case stuff? What does it look like? How do I fix this? I can't just do my right rotation. Right rotation is going to leave me with a still a broken tree. So I need to do something to this tree to fix it. Now keep in mind, before we did our rotation, we were able to predict that this was going to be a problem. Because right off the bat, pivot and culprit, before we ever did a initial rotation, pivot and culprit were set up for failure. Make sense? So if we connect these back up, here's pivot and culprit. And here's parent, and here's grandparent. So before we even try to put this guy into our right position, we can detect this is going to be a problem. Because we can notice that pivot and culprit have identical payloads. Okay, so what's the fix? Let's not rotate it just out of hand to be a right. We might need to manipulate our tree a bit more first. So let's throw a curveball here. Instead of pivoting about pivot, what if we did something relative to parent? Let's move up the tree a little bit and see what we can do. We essentially need to, we treat this like a Rubik's Cube. We need to do a couple of twists and then check the tree again and see, are we in a better position? Go ahead.
Set parent to where the grandparent is. And just rotate it like that.
Okay, so you want to effectively in our tree here make B the new root and drop everything off of B. Okay, so if we do that, if we make parent, now actually let's not mess with root right now because that makes the assumption it's the top of the tree. It's the local root, so you really want to have grandparent. Okay, what you really want to do is you want to have this tree, so really grandparent, you want to add grandparent to parent, which would then position it down to the bottom left of this. Okay, but then we've lost out on what's above here. We have great grandparent. Do we need great grandparent to make this work? Let's say potentially. Now, if I do that, just in our tree here, so in this case, we don't need a great grandparent because it would have been null. So we can go down this this line anyways. So we can ask, is the root of the tree equal to the grandparent? If it is, we can then set root equal to this new guy, set grandparent's right node equal to null, and then add grandparent to root, which would drop it in over here to the left. And now our tree is no longer out of balance. Okay, we did a rotation that wasn't like part of the normal rules, but it fixed the problem we were going to run into anyways, right? So if we come in and we notice that grandparent is the top of the tree, it's equal to root. We set root equal to this guy, set grandparent's right node equal to null, and then ultimately drop this to the left. Now our tree is back in balance, at least for one more move. And this is legal. All right, so we didn't do our normal transition, but still worked. Okay. What about if something did point to grandparent? So that takes root out of the equation. Let's see, can we create that? I need to throw one more A in here, like that. So now we're technically not out of balance for the moment, but then I'm going to throw in another All right, so no. Because we had this on the right-hand side that we're out of balance. We want to keep it being, we want it to be right-left. So we need grandparent to be on the right-hand side. So that means that, let's see, this would be B, B, B. Can we do that?
It would have to be A. We're trying to keep it on the right side. And
Then we have to fix the right-hand side. So then this would be an A.
That would be a C.
Oh, right. To make it bigger, so that's now off of this.
And then B, and then
And we wouldn't have that B, right? So now you have culprit, pivot, parent, grandparent. Hey. Oh, we're back to the same.
Weren't you trying to make the A great grandparent?
Oh, so we can do, I am. So we can do another D down here.
Or go back with the third B on the left side and just have A on the left side of parent or the grandparent, and then everything coming down to the right so it's unbalanced. And then the C coming off the B.
The C coming off which B?
The first B.
This C?
Yes.
But then we're not right left out of balance. We want to make sure we mean what I'm trying to accomplish here is a right left out of balance with a great grandparent for our special case. G grand. So this would be less than or equal to, so these would be A. C is to the right. D is to the right. D is to the left. D is to the left. Does this do it? 1, 2, 3, 4. Oh, yeah, we need. Well, now it is. If I take this A off. Is that a right left out of balance with a great grandparent? And is this a legal tree? So A, add 2 more A's, it'll all bounce to the left, then we'll add a C, then we'll add a D, then we'll add another D which goes to the left of the D, and then another D which goes to the left of the D. Okay. Think so? I think this is a right, left, out of balance with a great-grandparent. Okay, so it's definitely right, left, out of balance. This looks like a legal tree. Now we'd have a culprit that's here. We have a pivot that's here. We have a parent that's here. We have a grandparent that's here. And we have a great-grandparent that's here. And before we go any farther, I want to consider, is this tree possible if we're rebalancing after each time? What order would we have to add stuff in? We can add A, then C, then A, then D, then A, then D, then D. Yeah, it's possible. We can, in the right circumstances, we could generate this tree without ever having to rebalance until right now. So that's good. All right, so this is a good test bed. All right, so now we have our sample case where we notice that or special case rather, where we notice that culprit and pivot are the same. So since these guys are both the same, we know we need to go into special case mode. And special case mode, as you pointed out, should have us rotate about the parent. Correct? That's your theory. Is that our parent becomes kind of the new local root in this little world. So you want to have, and just for the sake of argument here, let me just create a copy of this, and let me just delete these arrows for this one just so they're not in the way. You want to do, this was parent, you want to create this. Let's see, how do we need to create that? You want C to drop into D. So that'll go left, left. Well, actually, that's not what you wanted. Where is that? You want to add the great-grandparent to the grandparent as its left tree.
Yeah, so it'd be just taking
It'd
it'd just be taking one down from the root and making that the new root.
You want that.
Yes. But when I said it, it was the parent switching to the grandparent because the grandparent was the root.
Okay, so if we have a great-grandparent, add the great-grandparent to the grandparent.
Yes.
If we don't have a great-grandparent, add the parent to the grandparent.
Add the grandparent to the parent.
Correct, yeah. Add the grandparent to the parent. So in this case, we have a great-grandparent, so we want to add the great-grandparent to one level down, which is the grandparent. If we don't have a great-grandparent, then you want to add the grandparent to one level down, which is the parent. Is it possible for us to have a right, left out of balance where we don't have a grandparent either? And have this still be a thing?
To have a right left out of balance with no grandparent.
Woo. Magic. Let's get rid of that for now. So that is a right-left out of balance where we don't have a grandparent. And it's also, this will produce an illegal tree. So in your world, then, you would notice these. You would say, well, we don't have a great-grandparent. We don't have a grandparent. So we're going to take whatever we do have, the highest level that we do have, and we'll add it to one down. So in this case, we're going to add parent to pivot. So D will go to the left of F, will go to the left of F like that. And then rebalance the tree.
Yes, but then wouldn't it still be illegal?
Oh, it would be as soon as we rotate it. Yeah, so, because that's going to drop down there. All right, so good thought. Seems like it works at the grandparent and great-grandparent level, but we didn't really push the issue. We potentially could make it so that it would produce illegal trees. All right, so for Tuesday, consider this problem. Come back with a potential solution. In fact, we'll do a quiz on Tuesday related to a potential solution to this problem. The grade on the quiz will not be whether or not your potential solution is the correct solution. It'll be related to whether your potential solution is a well thought out possible solution. So for instance, that would have, you're not allowed to use that one. But that solution would have been a reasonable quiz answer. Upon tracing the rabbit hole, we determined it wasn't going to work. Okay, so I want you to consider this problem over the weekend and come back on Tuesday ready for a quiz to present your possible solution. Make sense? All right. I will see everybody on Tuesday.